So DeepSeek just released something that, honestly, might be one of the biggest upgrades to how AI brains are built. Because for years now, the main strategy has basically been, if you want a smarter AI, you make it bigger. More parameters, more training data, more compute. And it worked. But then we hit a wall. These models started getting so huge that running them became insanely expensive. It's like trying to power a whole city just to answer a question. So the AI world created this trick called mixture of experts. And to keep it simple, the idea is, instead of using the whole brain for every sentence, the AI only turns on a few parts of the brain at a time. So the model can be massive without needing massive compute every single second. That was the big cheat code for scaling. And most people thought this was the future. Except DeepSeek is basically saying, okay, cool, yet you're still missing something important. They're saying even the best AI models still don't really have something that humans have naturally, real memory. Not memory like ChatGPT remembers your name. I mean something deeper. The ability to see something familiar and instantly recognize it instead of rethinking it from scratch every time. Because right now, even the most advanced AI models still do something incredibly inefficient. They constantly relearn the same simple things again and again inside the model while thinking. And DeepSeek is saying, that's a waste. Let me explain it like this. Imagine you're reading a sentence and it says, Alexander the Great. Your brain doesn't compute who that is from scratch. You don't go like, Alexander, ancient, Greece. Okay, let's see. No. You instantly know it. It's stored. It's fast. It's automatic. Now compare that to how language models work today. Even if they've seen Alexander the Great millions of times during training, when they see it inside a sentence, they still spend a surprising amount of effort rebuilding it internally. It's like having a friend who, every time you mention a celebrity, they act like it's the first time they've heard the name and they need to reconstruct the identity from clues. It's inefficient, and this becomes a huge problem at scale, because the internet is full of repeated stuff. Names, phrases, locations, expressions, common word combinations, things that honestly should be handled by memory, not by heavy computation. So DeepSeek released something called Engram, and the idea is basically, what if the AI model had a fast memory module for common patterns? So the main brain can stop wasting time on simple stuff and focus on real thinking. That's it. That's the whole philosophy. Now here's how Engram works. Explained normally. DeepSeek looked at something old school from before modern AI took over, from the early days of language prediction, engrams. That's just a fancy way of saying common short word patterns. Like 2-word patterns and 3-word patterns. Examples, princess of Wales, by the way, United States, New York City type of patterns. Stuff that repeats endlessly. Their idea is, instead of forcing the AI to recompute these patterns by running deep math through many layers, they built a shortcut memory table. So when the model sees certain patterns, it can instantly pull out a memory embedding for it. Kind of like a brain saying, oh, I recognize that phrase, here's the meaning blob for it. And the way they do this is actually clever, because obviously you can't store every possible phrase directly. There are too many combinations. So they use a trick that's basically like putting patterns into a giant organized warehouse using a hash system. Think of it like this. You have billions of memory slots. Each phrase pattern gets assigned a shelf number. And when the AI sees a phrase, it can instantly jump to that shelf and pull out what it needs. That's why the researchers call it constant time O1 lookup, which in normal language means no matter how big the memory gets, lookup stays fast. That alone is huge. Yet there's still a problem, because a memory system like this can sometimes pull out the wrong thing. The shelf might have similar patterns stored close together. It can have noise. So, DeepSeek added a second important piece. The AI doesn't blindly trust the memory. It checks it. It uses a little truth detector inside the model. So, when the memory brings information, the main AI brain asks, does this match what I'm currently talking about, or does it clash? If it matches, the model allows it in. If it doesn't match, the model suppresses it. In the paper, they literally describe it as a gate that outputs a value between 0 and 1. So in normal English, memory can be injected strongly or basically ignored. So this engram memory is not taking over the model. It's supporting it like an assistant inside the brain. Now, DeepSeek didn't just slap this on a toy model and call it a day. They scaled it to serious levels. They used the same tokenizer system as DeepSeek v3 with a huge vocabulary size, 128,000 tokens. Then they trained on 262 billion tokens. And if that number sounds insane, it is. That's basically like stuffing the model with a gigantic chunk of human digital civilization. The core brain is a 30-layer transformer with a hidden size of 2,560 and 32 attention heads. Then they combine it with that mixture of experts trick, which is already part of DeepSeek's system. So now you have two things. You have experts, which are like different specialists the model can activate, and you have Engram, which is like a fast memory. And the big question DeepSeek asked is, how much of our model should be specialists and how much should be memory? Because both take space. Both take parameters. You can't max out both endlessly if you want efficient compute. So DeepSeek formalized this as a real mathematical problem. And what they discovered is extremely clean. There's a sweet spot. If you give the model only experts and zero memory, it wastes time rebuilding simple patterns. If you give it too much memory and fewer experts, it loses brain power for deep thinking. So there's a balance. And that balance, based on their experiments, was roughly about 20 to 25% of the model's spare capacity should go into memory. Meaning, not everything should be experts. A chunk should be memory. And that's the big architectural takeaway. Now let's talk about what happens when they actually scale it. They compare multiple model versions. They have a pure MOE model at 27 billion total parameters. Then they build Engram 27B, also 26.7B total parameters. Same compute budget, same architecture backbone. Yet they reduce the number of routed experts from 72 down to 55, and they take those freed parameters and put them into memory. So Engram 27B includes 5.7B parameters just for memory. Then they scale even harder with Engram 40B. Same compute per token, yet memory grows to 18.5B parameters, total 39.5B. So think of it like this. They're not making the brain think harder. They're giving the brain a much bigger memory library, and then they test it, and Engram wins, across the board. On a major benchmark dataset called the Pile, the MOE model gets a loss score of 2.091. Engram 27B drops to 1.960. Then, Engram variants push 1.950. Then, Engram 40B gets 1.942. Internal validation loss also drops a lot too. The MOE baseline sits at 1.768, then Engram 27B drops that down to 1.634, and even the Engram variants keep pushing it further, down to 1.622 and 1.610. And then the benchmark scores go up in a way that honestly surprised them. Because sure, memory should help on knowledge tasks, right? Trivia, facts, all that. And yeah, it does. MMLU goes from 57.4 to 60.4. Chinese MMLU jumps from 57.9 to 61.9. C-eval goes from 58.0 to 62.7. Yet here's the wild part. Engram also boosts the stuff that feels like pure thinking, the kind of tasks where you'd assume memory wouldn't matter that much. Arc Challenge climbs from 70.1 to 73.8. BBH goes from 50.9 to 55.9. Drop F1 rises from 55.7 to 59.0. Even coding improves too. Human eval goes from 37.8 to 40.8. And math climbs as well, like GSM 8K going from 58.4 to 60.6. So overall, DeepSeek's memory module is improving reasoning, coding, and math. And at first that sounds backwards, because you hear memory module and you think it's just gonna help the model recall facts. So why would it improve reasoning? But DeepSeek's explanation actually makes a lot of sense. They say in normal transformers, the early layers waste a ton of effort doing basic reconstruction, basically rebuilding the same repetitive entities and patterns over and over again. Engram takes that boring, low-level work away, which means the model reaches useful representations earlier. And the best way to think about it is, it's like giving your model extra depth without literally adding more layers. They even back this up with mechanistic analysis. They show the model becomes prediction-ready earlier in the network. And in their CKA layer similarity analysis, they find that shallow Engram layers behave like much deeper MOE layers. One example they give is that layer 5 in Engram aligns with layer 12 in the MOE baseline. So, the model becomes deep faster, and that's a huge reason why reasoning improves, because it isn't burning its early layers on repetitive entity reconstruction anymore. Now, one more part where Engram becomes ridiculously important is long context. After pre-training, they extend the context window to 32,768 tokens using a method called YaRN, training for 5,000 steps on 30B long context tokens. Then they compare Engram and MOE across long context benchmarks. And Engram goes crazy, especially on tasks like needle in a haystack, where you hide something inside a massive document and test whether the model can actually find it. Multi-query needle in a haystack jumps from 84.2 to 97.0. Variable tracking goes from 77.0 to 89.0. So Engram doesn't just make the model smarter in general, it makes long context work better too. Because when Engram handles local pattern memory, attention becomes freer to focus on global context instead of wasting itself on small repetitive stuff. And then we get to the last insane part. System efficiency. Because people always ask, cool research, yet can it actually run in the real world? DeepSeek shows Engram is designed in an infrastructure-aware way. Since the memory lookup is deterministic, the system can know what memory it's going to need before the model even reaches that memory layer, so it can prefetch it in advance. They run a test where they insert a massive 100B parameter Engram layer and offload it entirely to CPU memory, and the throughput hit is tiny. A 4B dense model goes from 9,031.62 tokens per second to 8,858.28. An 8B dense model goes from 6,315.52 to 6,140.02. So worst case, it's only about a 2.8% penalty. That basically proves you can bolt on ridiculous amounts of memory and still barely slow down inference, as long as the system is engineered properly. And finally, they visualize how the memory gate behaves. And it activates exactly where you'd expect, on entity completions and common phrases like Alexander the Great and Princess of Wales, even in Chinese on famous historical expressions. Which means the model is genuinely using memory like a real pattern recognition system. Alright, that's it for today. If you want more AI breakthroughs explained in plain English like this, subscribe, drop a like, and I'll catch you in the next one.